Right. What I thought I'd do initially this week is to just quickly run through a little bit about the practical analysis for your reports. I'm not going to spend too long on it, but what I've done this morning, and I'm conscious of how much you guys have been talking about how far your results are out from what you designed. One thing you have to remember, the constant K filter is quite a simple design filter. It's not that complex. There are other designs you can do with LC, but we really don't have the time to go into, nor do we have the components available, at least not at the moment, to go into trying some of them other designs to see if we can improve. And that really isn't the point of what we're trying to do anyway. We're trying to just get the basics of filters over. So what I done this morning was I quickly went for a low pass 600 ohm with an FC of 100k, and just saw what I could achieve. This turned out to be to 1 millihenries in series to get that value, and these were 2 times 0.47. 2 times 4.7 picofarad in parallel. In series. Yeah, to get that value. So each side I had 2. So that's a circuit with quite a few components on it, which is probably going to make things a little bit worse because there's more tolerances of those components to consider. And it actually did turn out to be that way. It was quite a bit further away from 100k than I expected, to be honest. So what I then did was analyse using LC, and looking at that at 100k with the preferred values that I'd chosen, that was predicting that I'd get about 0.03 of a dB attenuation in the pass band. The design frequency 100k, I got about 2.9 dBs of attenuation, and the 3 dB point predicted was at about 100.23, which is very, very close. I thought should be close here. Yeah. So then I came in here and done the experiment like you did. I put the circuit together, connected it up to the scope, done all the things you did last week, and I got the following results, which looked, outwardly to be fairly reasonable. I took readings at every half a decade from 500 hertz to 1 meg. You'll notice all the way that I'm consistent here. We can measure on the oscilloscopes to 2 digits. So that's all I've included, 2 digits. I've included 2 digits right through, even where I haven't put 0.9, I put 0.90 to say that's exactly what it was. Okay, and I've calculated the attenuation on the end there using 20 log V out over V in. Yeah, and that's actually quite easy, really, because I chose 1 volt there. That's whatever that is over 1, so I just put that figure there into that formula inside the brackets. Okay, so I've got attenuations there, 0.35, 0.35, 0.35, 0.92, so I start on a move at 50k. Yeah, and then I got at 100k, I got 7.1 dB, which is quite a way over the 3 dB we'd expect. We haven't got much attenuation in the pass band, which is encouraging. And then down here, 14 dB at 50k, I'd expect that. And at 1 meg I couldn't even measure the output, and I think that's what you guys are getting, won't it? You won't measure anything really, apart from noise, when you put a voltage in at 1 meg.
Is that 500k or 50k?
Should be 500, Carl. Well spotted. Put that together rather hastily this morning. Okay, so that's at 500k. So having done that, I went off and got myself some log linear graph paper, and I got a copy of this for you, if you can't, in case you can't see it very well. And I put, I got some 5 cycles, so I'm starting at 0 here. There's a K, there's 10k, 100k, 1 meg, 10 meg on the frequency scale, which is the logarithmic scale. 0 to 30 odd, 35 dBs attenuation on the linear scale. Up here, these are all my ones that are 0.35, starting to turn here. Although when I put the curve in, I thought that one's a little bit rogue, appears to be a little bit away from where I might expect it, because these two created a nice slope for me down. Why can't I get the magic pen up? Don't want to work. Anyway, right now. That parameter is not going to work, is it? We're talking about the slope there. Sorry about that for anyone watching the video. So, having drawn in a best fit curve and I know what sort of shape it should be, yeah, I've then gone across from 3 dB here, drawn a dashed line across to there, down to the bottom, and I'll give you a paper copy, estimating somewhere around about 40-45k, which is a considerable distance away from what I designed. Could be down to the multiple components, not looking overly successful. But what I could do, if I was writing the report like you are, is then go on to talk about how I might experimentally adjust that. By use of the software tool has at least given me a starting point. I could go off and try more complex designs. I could add, you know, in LC you've got that thing with stages, the number, let's just get it up.
What was your original cut-off frequency specification?
100k, Carl. Hang on, where's LC gone? Better in on here, is it? Let's just. What you could try in LC is my 100k in there, 600 ohm, and add more stages to the schematic. So you're add on a second stage. You can see that brings in some different value components. We got 5305 picofarad. They're the ideal values for the wave. Okay, so bringing in more stages to the filter, and that's what the effect that should have in adding stages is to increase this roll off here. That would have the effect of doing that. So you might, if you've got time, you might like to just investigate that. You're not going to investigate it practically, but you could investigate it using the software. Okay. The conclusion. Yeah, towards the end of it, further things that could be tried to achieve closer to what you wanted in the first place.
Yeah, so that's the whole point of a report, isn't it? It's not just to say what happened and what went wrong.
Having said that, let's say if I designed this filter to get rid of 100 kilohertz ripple sitting on top of a 20 kilohertz signal, So we've got an AC sine wave that we want, this 20k. Let's just make another slide. If we had an AC signal where we got this, right, and this bit that shape, let's say 20 kilohertz is what we're looking for, right? But this ripple on the top here is 100 kilohertz, and we don't want it. If we pass that through my filter, that would ably get rid of that 100 hertz off the top there, filter that out, and we'd end up with just the red part. So it would fit that purpose. Do you see? It all depends on what purpose you're designing it for. And you know, with any design, you know, if you've got to be really close to it, you're going to have to get a more complex circuit than if you keep it simple, if your application needs aren't that stringent. And I haven't given you an application to work to, because the idea of this is for you to contrast between what you wanted in the first place, what the simulation said you was going to get, and then what you actually get when you build it. And partly to know that you aren't going to get it that close, and you're going to have to make some more adjustments. And within the time frame that we've got to do this practical, we do as much as we can, but we haven't got time to go around and try umpteen different designs. Okay? The other thing you could try, and have a look at, if you wanted to, is in ELSI, if you go back to the design page, and if you click on a question mark there, tells you a little bit about the families and what they do. So that, looking at the blue line, that's what you get with a constant K.
Like, where did you click for that? Oh, the question mark.
Yeah, the question mark, just there. And then you can change between the families, and it tells you a little bit about them. Some of the terminology, I have to admit, I'm not a filter expert, so I don't understand all of it myself, okay? But there's the blue line that you get, okay? I'm not sure what the red line is indicating. If we go M-derived, I do know a little bit about what M-derived does. It adds a little resonance circuit in to the situation. You have to give some extra specifications. And that's what gives you this very steep roll-off, which then comes back up to meet what you would have got with a constant K. That's like a constant K with a resonance circuit added to it. So you get this very sharp cut-off at your design frequency that starts to come back up a bit, but then meets what it would have done with a normal constant K. So you get a bit of a strange roll-off like that too.
So would you use that if you had, say your system was particularly delicate to a certain frequency?
Yeah.
If you needed to
but you'd have to take into account that you're going to get that at those frequencies.
There might be like Mark was talking about where you get superposition of waves and you get a natural frequency.
Yeah,
so
I don't fully understand that, but that you actually select a second frequency slightly higher, and that's got something to do with how deep and where this sharpness goes. I haven't experimented with it because I haven't had time. But that's a family that you could try.
You'd use that where, like, say, like on our systems, you'd get sometimes you pick up noise on certain frequencies. If we had like multiple frequencies, you could use something like that so that you get a range of frequencies.
If you
knew where the noise would be, is where it
if you knew you'd got something there, you could actually cut that out, and you aren't really bothered about this. If you know you haven't got any frequencies up here, it don't matter, does it? I don't know how to pronounce that, but Kawa, that's the type of shape you get. Butterworth looks like a constant K. It's got a flatter pass band. Okay, so there's some areas there that you could look into. Bearing in mind you only got a certain number of words, and I'm only talking about suggestions of what you could look at. Okay? And I thought, well, I'll just put that together, and maybe a little bit of help to see what for you to complete your assignments in time for. Was it next week? I think, wasn't it? Yeah. Okay. So, any further questions about that before we move on to the main topic of our session today?
Are we not using today for more